Today we're going to talk, move forward here, friction and wedges, which is not on the upcoming exam, but it will be certainly on the final exam. Our learning objectives here are first to write the relationship between what's called the friction angle and the coefficient of friction. You all have heard of the coefficient of friction before. That's that mu term. And then also describe that relationship with the normal and the frictional forces. We'll talk about all of that stuff. Determine the direction of the frictional forces with respect to impending motion. Impending motion is going to be really important for us in this class. And then draw FBDs of blocks and wedges that can be used to find unknown forces, and use the equations of equilibrium to find forces for impending slipping or tipping. So our homework problems here, you're going to see some like rigid objects, multi-force rigid objects and two-force rigid objects in these problems, along with friction on top of that as well. So we're kind of friction problems with a statics flavor to them. So in this one, trying to find the smallest P to stop the wheel, subject to a couple moment there. This one here, we have a ladder, and they asked to find the coefficient of friction given the weight of the man and the angle theta there. And then number 3, find theta for which motion of the blocks is impending. We're going to do a problem similar to that in class. And then this one is to find the smallest P to cause the crate C to move upward. Take a look at the Canvas calendar. Remember, the Canvas calendar is really nice for keeping track of like what handwritten homework is due and what mastering stuff is due. If I remember, I was looking at it earlier. If I remember correctly, this homework is not due until after the exam. So let's take good notes so that you have those and use those when you're working on this after the exam. And then also on this one, it states on mastering, and I just want to reiterate, so nothing you have to write down, but assume the crate only moves in the y direction and that wedge A cannot move. So just watch out for those statements there on those homework problems. And then going back to this one, find the theta for which motion of the blocks is impending. Let's talk about how we would solve that. And I want to do that with a friction race here. So I'm going to show a video. Actually, this is a video. I asked my 11-year-old last semester, I was like, you want to do a video for my class? I like to show these videos every once in a while. And he's like, okay, sure. So what this race is about is he's going to lift up that board, and let me start polling here as well. He's going to lift up that board, and I have 3 masses that are sitting on that board. They're all the same type of material, right? Between those masses, they're all painted with the same paint. They have different surface areas, and they have different each masses. You can see a small one, you can see a medium one, and you can see a big one there. So small is A, B is medium, and C is big. What I want to know with this poll here is, I'll relaunch polling. So maybe don't respond quite yet, but so what he's gonna do, let's see, I think if we could start it here.
Okay, so today students, we are doing math, as you can see right in front of me. This is math.
He's saying that this is math. That's kind of, okay. So he's gonna lift that board up, and then which one is going to slide first? It's not like which one's going to get to the end of the board. It's just which one is going to move first as he raises the angle of that incline right there. So A is the small one, B is medium, and C is big.
And so we're going to see which one is going to start moving first. Are you ready? Get your votes in. And
okay, so I think everybody, I got 51%. I'll go ahead and end polling there. Share the results. I didn't give you a lot of time to vote there. Sorry, I didn't realize it was going to go that fast right there. But the most popular choice was A. They said the small one was going to go first. And then 17% said B, 33% said C. So a little bit all over the place. And then actually 4% of the votes said D. Actually, I think D is technically, I didn't put it up there. I didn't want to make it super obvious, but D would be like, they would all slide at the same time. Effectively, well, we could have seen one slide a little bit sooner than the other, and the experiment is not perfect, right? But yeah, they all slid at the same time. And so the reason is because the coefficient of friction is the same for all three of those objects. So let's take a look here at our friction race. And let me zoom in just a little bit more, make writing easier here. So our friction race, we had these masses that were on this incline, and I'll just draw this as a block right there. And I'll draw the block where it looks like it's kind of floating here, just so we know that it is a contact surface, a sliding contact surface right there. And if we think about the forces that are acting on this, well, we have a W that's going to be at the center of gravity of each of those masses. And I'm going to call it a W for weight. We'll go into weight here instead of thinking about it as a mass there, but that's going to go straight down, right? And so that's what varied in each one of those objects. And then we had the angle. This is the angle. We were trying to say, okay, which one is going to slide first? Well, what we were changing is we changed this angle right here, theta. And so if we draw the FBD of this block, well, we know that our impending motion was down, right? And in statics, we are not going to think about things that are necessarily moving. They're going to be on the verge of moving, and so their motion is impending. So this is our impending motion is down the ramp. Well, what direction, if we're going to draw our frictional force on here, what direction should we draw our frictional force? Let me look at our front row here. How about Ted Kim? Ted, what direction is our frictional force going to go? Should it go down and to the left or up and to the right? Okay, Ted is not here. Oh, I see. How about Katie? Maybe Katie's not here. Ben Idler. What direction? So our frictional force go down and to the left or up and to the right?
I think it should be up and to the right.
Up and to the right, absolutely, right? Because our block is trying to slide down the ramp. Frictional force will always oppose impending motion. So our frictional force is going to go there. And then we'll also have a normal force that's acting between those two objects, right? Between the surface and the mass that's going to be sliding down there. Now, we could look at, we could look at our equilibrium equations, but there's a material property that really controlled in it. And what can we say about the force of friction? Can we say anything about what the force of friction is going to be equal to? Thinking back to your physics days or when you've dealt with friction in the past, what do we typically say force of friction is equal to? Anyone? And also, Ben, thank you for that response. Yeah, force times mu, right? Like coefficient of friction. Yeah, absolutely, right? So mu times n. So the normal time, mu times the normal force right there. Well, mu for all three masses is the same. And so mu is really a material property. And now, when can we say this? When can we say that the force of friction is equal to mu times n? Could we say that at any point in time? Like, even if I wasn't on the verge of sliding, like, what about when, before they started sliding down the ramp? Is the force of friction still equal to mu times n? Or is it's actually less than mu times n? So this is only when on the verge of sliding, or what we're calling impending motion. So if we are not on the verge of sliding, then we would say the force of friction is somewhere less than mu times n. And we would have to find the force of friction using equilibrium equations, not a material property relationship like we're showing over here, this mu times n. So we'd have to find it using our equilibrium equations there when we did that. So mu is exactly the same for all three of those. Now, I don't think you all have really talked about this in your previous classes, but there's actually a relationship, which was our first learning objective, between what's called the coefficient of friction, or mu, and the friction angle. So mu is equal to the tangent of phi. Phi is the angle at which sliding occurs. So all this time we've just been throwing out like, okay, mu is equal to what? Like what's like this first number that comes to mind? Like what's a typical mu? Typical mu is equal to what? Anybody? 0.5, right? Yeah, absolutely. 0.5. Well, what's the angle? What that corresponds with is if I took that object and we put it on an inclined plane and we measure the angle that it starts to slide at, that would be that's how we can actually find mu. And actually they run the tests that we use to find mu are tests that basically do that. They figure out how much force or they figure out what angle the sliding starts to go at. Now, if we wanted to find phi for this, can we find phi is going to be equal to the inverse tangent of 0.5? And if we plug that into our calculator here, inverse tangent of 0.5, that's a phi equal to 26.56 degrees. So that's probably similar to what we had, right? 26.56 degrees, but that friction angle Hey, I'm back. Okay, sorry about that. Where were we? What was the last thing that you all heard? Did everybody write down the 26.56 degrees? Okay, so we wrote down, we got the 26.56 degrees. Okay, so we're good. So I have seen friction angles all the way up to like 48 degrees. But what if phi is equal to 45 degrees? Oh, is my audio bad again? Or now, not again, but let me see what. Man, I'm still on my same microphone. Okay. Okay, so I've seen friction angles even above 45 degrees. When we have a phi of 45 degrees, what is our coefficient of friction? It's equal to 1.0, right? So we take, and we write out the equation here. The tangent of 45 is equal to 1.0. So that's basically saying everything that goes, our 100% of our normal force turns into frictional forces. And so in that case, what usually ends up happening though, when we get really high friction angles is in these systems, we usually end up with slipping and tipping going on. And so like this was for, I saw this friction angle of 48 degrees at the contact interface between a concrete dam and the foundation rock. And what usually ends up happening in that scenario is like the dam will slip a little bit, like during an earthquake, the dam would slip a little bit and then it would tip a little bit. And it'd go back and forth between like these slipping and tipping modes. And so actually that throws us into our next example here, or into our example, we'll look at slipping and tipping. But I want to go, actually, before we do that though, I want to go back to this homework problem, which I said this was related to. They're asking you to find theta for which motion of the blocks is impending. Well, they give you a mu and they give you a mu. So we don't even actually have to do any equilibrium equations. We just know that the relationship between mu and the friction angle is based on the tangent of phi. Okay, like we showed in our friction race here. All right, so let's jump in to an example here where we have a crate, and this crate is going to be sitting on a horizontal surface here. We're going to apply a force P right here we're going to find. And then we have the weight of this crate, which we are told is equal to 200 pounds right there. And the dimensions on this are, and actually technically the center of the crate would be right there. That is a distance of 3.5 feet and 3.5 feet. So we have 3.5 feet and another 3.5 feet. And then horizontally across here, we have distances of 2 feet. So this is a 2-foot dimension, and then this is also a 2-foot dimension right there. And actually, I'm going to leave some room below this so we can draw our FBD right on top of this, on top of our given information. We are asked to find, for this problem here, the A, P for impending motion, and then part B, we would like to find H, so it tips and slips at the same time. And let me define H over here on our original given information. H is the location of where we apply that force P right there. Rolling motion referring to like tipping and slipping at the same time. It's more of like a transition between the different failure modes of a sliding failure mode or a tipping failure mode in response to your question in the chat there, Colin. Okay, so we're also given in this problem here that mu is equal to 0.4. And so that would be along this contact along the floor right there. Now, so let's draw on top of here, let's draw our free body diagram. So when we're looking at something that's on the verge of tipping, and actually let me just use this ruler here. if it's on the verge of tipping, then where does the normal force go? When it starts to tip, and we've talked about tipping in 2D rigid body equilibrium, doesn't the normal force go to the corner, right? Yeah, it goes all the way to the edge there when we're on the verge of tipping. So let's draw our normal force right there. And then our frictional force, remember, is going to oppose impending motion. Our impending motion is to the right. So our frictional force is there. And can we say that it's equal to mu times n? We can say that it's equal to mu times n. And that's because they tell us the P for impending motion. So that's when we know that our force of friction is equal to mu times n. For our solution here, we can find for part A, what if we just sum forces in the x is equal to 0? We got positive going to the right. Let's say we're going to have a P minus our force of friction is going to be equal to 0. And so then we can continue our solution over here. We basically got P is equal to mu times n. Well, what is n equal to? We can find n by summing forces in the y equal to 0. And so we're going to have a minus 200 plus n is equal to 0. Our n we know is equal to 200, which then back up to here, we can find that P is equal to 0.4 times 200, or 80 pounds. So we're using two things, right? We're using our material property, the force of friction is equal to mu times n, and we're also using the equilibrium equation, sum of forces in the x and sum of forces in the y. Now for part B, we need to figure out H so it tips and slips at the same time. When we're in a tipping motion, we're going to sum moments. And where is it going to tip about? It's going to tip about that corner. And so let's sum moments at the corner and set them equal to 0. So when we sum moments about the corner, I'll label the corner over here. The force of friction and the normal force both go through that corner right there. And so what do we have going on? We have our 200 pounds at a distance of 2 feet, and it's going to cause a positive rotation. And then we have our minus P times that distance H, which is what we're looking for. And so when we solve this, we know P is equal to 80 pounds. We're going to find that H is equal to 400 divided by 80, which is 5 feet. So when we're looking for tipping stuff, we're looking at summing moments. When we're looking for slipping stuff, we're looking at summing forces, because that's the motion that we're impending, right? That we're on the verge of occurring. Okay, any questions about that problem? All right, let's look at now another example problem here with these wedges. So wedges usually have angles, right? That was all like horizontal and vertical forces. What about now if we looked at something like this? And we have a wall and a floor right there. And then we'll put a wedge down here. And actually it's going to be at a 45-degree angle, this right there. So we'll put a wedge that's right there. And I'm showing them floating, but that's just to make sure we know exactly where the contacts are. And then there's going to be another wedge that's right here. And it's touching the wall over there. And we're going to have the weight of the wedges is going to be negligible, but there's 750 pounds that's sitting on top of that wedge right there. And we're going to apply a force P to this wedge over here. And we're going to want to figure out what that value of P is. We have some information on the geometry. This is 45 degrees, which means that this is also 45 degrees. We'll call this wedge up here. This will be wedge A, and then this will be wedge B, will be that one right there. We're given that mu S, it's our static coefficient of friction. It's possible we'd see kinetic coefficient of friction, it doesn't matter. We can see problems where there's a constant velocity. We treat them exactly the same, but we're not looking at like a transition between static and kinetic or anything in this class. It's either going to be in static motion or basically no motion, static, or it's going to be in constant velocity. So our mu S for this one, for all contacts, is 0.25 for all contacts. Oh, did somebody, was I cutting out again? I feel like my internet, I was having some issues this morning too. That's what I'll do this weekend. I'll reset all my routers. Okay, so mu S is 0.25 for all contacts. We want to find two different parts here. Part A, they're asking us to find the min P to raise A. And then part B is the minimum P, so A doesn't fall. So those two parts, what they change is the direction of impending motion. It drastically changes the value of P that we're going to find. The P for part A is going to be more than 2,000 pounds. The P for part B is going to be around 200 pounds. So by changing the direction of impending motion, all the values change by a significant amount. So let's look at how we are going to solve these problems. Again, our FBDs are really about identifying all the possible options and then picking the best one from those options. In this problem where we have two different wedges, we could do an FBD of wedge A, we could do an FBD of wedge B, or we could do the FBD of both of them together. Which one has a known load? Which FBD has a known load on it? It's the FBD of A, right? Yeah, so, okay, so we would, so B doesn't have a known load, right? So we can basically think about, okay, we identified all the options, but then we use this intelligent enumeration to figure out which option should we consider first. Well, if we did an FBD at A, and actually that's where we're gonna start here, and then after we draw the FBD of A, I'll also talk about the FBD of A and B together. That's an option because A and B together does have a known, but unfortunately it's gonna have 1, 2, 3 unknowns. And we don't have any distances here. We know 45-degree angle, but we don't have any distances, so we can't sum moments, which means we only have two equations of equilibrium. So our FBD of A, and this is for part A, so that's going to tell us the direction of impending motion, right? The min P to raise A, and so our impending motion is going up. So that's going to help us. We know what direction it's going. That's going to help us draw all of our frictional forces, make sure those are in the correct direction. Now, we have our 750 pounds that's going here. We're going to have a normal force here. Let me call that N1. We'll have a normal force along there. They're always going to be perpendicular to the surface, right? Normal along 2 as well. And we know that is a 45-degree angle. And so we have our 2 normal forces, and we can, based on the direction of impending motion, we can draw FF1, the force of friction at 1. So we know it's going to be parallel to the surface, but which way should it go? Should it go up or should it go down? Let me see if I can find somebody else from our front row here. Kristen Mazarin, I think you asked a question earlier. Kristen, which way should force of friction 1 go? Should it go up or should it go down? Okay, let's. How about Preston Miglaw? Nope, not here. Okay, anybody? The force of friction should go down, right? It's got to go the opposite. It'll always go the opposite direction of our impending motion. So we're going to have this FF1. Now, can we say that it's equal to mu times n? Is that valid? Are we on the verge of sliding? How do we know if we're on the verge of sliding? Based on our problem statement, anytime we see minimum, maximum, impending, like we saw in the previous one, that means that it's at the limit. And that mu times n is at that limit when we're at the verge of sliding. So yes, that one will be equal to mu times n. Now, how about over here at n2? That one also has to oppose impending motion. In general, impending motion is going up. So our FF2 over here is going to be equal, or is going to be going down to the left, and it's going to be equal to mu times n2. Okay, so we have our FBD of A. Technically, this has 2 unknowns. And the reason I'm saying 2 unknowns is because isn't FF1, that's really a function of N1 right here. And then FF2, that's really a function of N2, isn't it? So really not like FF1 and FF2 are unknowns. It's that they're functions of N1 and N2. So we really have 2 unknowns in this FBD. And so we can solve those 2 unknowns using sum of forces in the X equal to 0 and sum of forces in the Y is equal to 0. When we do sum of forces in the X, we're going to find an N1 minus an N2 cosine 45 minus FF2 times the cosine of 45 equal to 0. And I guess I'm saying that our FF2, the angle that I'm using for FF2 would be from the vertical here. So there's I'm using that 45-degree angle right there. And then sum of forces in the Y, we're going to end up with a minus 750 minus FF1, and then a minus FF2 times the sine of 45, or no, wait. Let's see, cosine of 45. No, this should be, sorry, I should flip these. This right here should be sine of 45, and this one down here should be cosine of 45. And then we're going to have also a plus N2 times the sine of 45 is equal to 0. So we sum forces in the X, sum forces in the Y, taking into the angles into account, and we would find that N1, we got 2 equations with 2 unknowns. We're going to find N1 is 2,143, and 2 is equal to 2,424 pounds. Okay, so now we can go on to the FBD of B. And because we know N2 now, so here's the FBD of B. We have our P that we're trying to find right here. We'd have this normal force, which is going to be always a pushing force. So it's going the opposite direction that we drew it over here, but it's N2, which we know is 24 pounds. We'll have a new normal force along the floor here, N3. And so again, we can figure out our frictional forces based on the direction of impending motion. Our impending motion needs to go to the left, right? Because what would have to happen to block B in order to raise? Remember, we're doing part A, and part A is to raise min P to raise A. So A goes up. Well, that means that B needs to go to the left, doesn't it? And so our impending motion for B is to the left. And so then that tells us what direction our frictional forces need to go. This FF2 right here is going to go up and to the right. And it would be equal to mu times N2, which we already know. And then our FF3 right here is going to go opposing impending motion and be equal to mu times an N3. Again, we have two unknowns. In this case, our two unknowns are N3 and P. We could sum forces in the X, sum forces in the Y, and we would find that when we go through that exercise, we would find that N3 is equal to 1,286 pounds, and P is equal to 2,464 pounds. So there's our minimum value of P to raise A. And what that means is that it's right on the verge, right? It's about to start going up. If I applied one more pound, it would start moving. But since we set everything to, we set all of our frictional forces to the limit of mu times N, we're right on the verge of moving. For part B, so part B was so that A doesn't fall. Well, the only thing that changes, which changes everything else, is for that part B, we're going to have our impending motion on this one is going to go down. Well, doesn't that change the direction of FF1? That changes the direction of FF2. It's going to change the value of all of our normal forces. For this one, our impending motion is now going to go to the right for block B. That changes all of our normal forces, all of our frictional forces. And for part B, we're going to find that P, we only need 228 pounds. So to hold everything in place and prevent it from falling, we only need to apply 228 pounds. But to overcome all those frictional forces and be on the verge of sliding up, we need a lot more than the 750 pounds that are applied to that wedge there at B.